Okay, so we have already talked about simplifying radicals, and I know that that was something that really shouldn't have been new to you anyway, but this is a good tip sheet that kind of covers all the different things that are going to come up, some of which I have already covered with you, some of which you have already learned, but not necessarily all of it, and not in a comprehensive manner like this. And this would be a good sheet for you to refer back to even in years to come when different things come up if you're unsure about what to do with square roots so that you don't do crazy stuff. So before we ever even start talking about radicals, let's just talk about this first little sentence here and what the terminology means in this. So it says to simplify a single term radical expression or a product or quotient. Okay, so let's just recap here. Radical is just a square root. That's root. Expression, difference between an expression or an equation, that means there's no equal sign. It's just like a term. We're adding a couple things together, but we're not simplifying an equation or solving for anything necessarily. Okay, product, that is the result of multiplication. And quotient is the result of division. Okay, so all things that we should know, just make sure we're all on the same page with that. So to simplify that, we're going to make sure that there are no perfect square factors under the radical, make sure that there's no fraction under the radical, and make sure that there's no radical in the denominator. Basically, when you are simplifying, you are reducing it, kind of like reducing a fraction. You're changing the way it looks, but you cannot change its value. That's what you have to keep in mind. The value is the same. So one thing that the calculator actually can help you with on this, it won't give you the answers, but it can help you make sure that the value of what you finish with is the same as the value of what you start with, as long as you type everything in correctly. Because I want you to think about this. Let's think about if I give you the fraction of 4/8. I know that's not a square root, just stay with me here. And I say, okay, reduce that fraction. All right, well, I can reduce that to 2/4. So have I reduced the fraction? Yeah, I reduced the fraction. Did I reduce it all the way? No, I did not. So even though this is a reduced version of this, it's not reduced all the way. And the same thing can happen with square roots. You might take some things out and you might reduce it and it still has the same value, but you didn't finish it. So that's when it says no perfect square factors are under the radical. You can take some out and leave some in by accident, so you're still not finished. So if I was going to reduce this all the way, this actually gives me 1/2 in the end. So all three of these fractions look different. If you glance at them, they don't even look like the same fraction, but they all have the same value. So the same thing happens with the square roots. They're not going to look the same after you simplify them, but the value is still the same. Okay, so let's just look at these. We're going to fill in some stuff on here. So I've given you examples on the left of what the problem might look like and what you come up with, and then on the right it tells you what to do. And you've got some options. You've actually got a few options on this one, and we're going to look at it all three different ways because you all still may be kind of some different levels of this, and I'll tell you when certain things are okay and when they're not, and when you can stop and when you can take shortcuts if you're ready for that sort of thing. So we're going to start by just doing the full tree with this, all right? And I'm going to have to do it sideways because I didn't give you enough room here. So tree, just like I showed you the other day, we're going to look for 2 factors of 32. Okay, so I'm going to use 4 and 8. All right, well, neither one of those are prime numbers, so I'll break that up again. 4 can become 2 and 2. Those are both prime. 8 can become 4 and 2. So 2 is prime. And then 4 has to become 2 and 2. And then I circle them all, right? So then I look for pairs. And I've got 2 2's here, comes out as a regular 2. 2 2's here, comes out as another regular 2. And this 2 has to stay underneath the square root. Multiply everything outside together, everything inside together, and I get 4 square root of 2. Okay, so that's the full tree way. Now, again, I know that some of you were taught, and it's fine if you know it, and this is a good one to do, where you look for the biggest perfect square that would divide into 32. So let's do it that way. So if it's 32, I know that 2 factors of 32, 2 factors of 32 are 16 and 2. Okay, well, 16 is a perfect square, so I don't have to keep splitting it up. I just take the square root of that. Square root of 16 is 4. That's where that comes from. And then 2 stays underneath. One other way to look at this, let's see if I can figure out where to write it. Guess I'll do it over. Oh, I don't think you can always see that. Yeah, I'll do it over here. Square root of 32. Square root of 32. Okay. So let's say I start the tree and I do the 2 and the 8. Okay. And then, not the 2 and the 8. Oh my goodness. I'm so worried about making my pen work. It's not 2 and 8. 2 times 8 is 16. Come on. If I did this, what I meant to say was 4 and 8. Okay, so 8 then becomes 2 and 4. And then 2 is a prime number. But then 4, it's not prime. And over here I kept going. But even though these are both perfect squares, whether they were or not, it doesn't matter. I can keep reducing them, or since it's a pair, even though I haven't finished it all the way up, I can stop there and find my pairs. I cross out my 2 4s. They come out as a 4 right here, and then this 2 stays underneath, and I get the same answer either way. Okay, next one. It says if we have 2 square roots that are multiplied together, and you've got a couple of options of what you could do. It says that we could multiply the numbers together and then split so you have a perfect square factor and another factor, or split each number into factors and remove perfect square factors or pairs of factors. Basically, here's what we can do. We can multiply everything underneath the 2 square roots together, and that's totally legal. But then I know I'm going to have to simplify. So if I multiply these two together and get a big number, right? Let's think about what this number would be without having to go off to the side and do this. Learn how to split things up. 8 times 20 is 160, and then 8 times 2 is 16, and so 160 and 16 will give me 176. So I get the square root of 176. Not a perfect square, and not anything necessarily that you know 2 factors of, except I do. 2 factors of 176 are going to be 22 and 8 because that's how I got it. So if I multiply it together, I'm going to have to take it right back apart. So I'm just not even going to worry about doing that since I know I have to simplify. The easier thing to do really at this point is to go ahead and just start breaking this up. And I can make this into 2 and 11. Those are both prime. The 8 becomes 2 and 4. And the 4 becomes 2 and 2. So since they're going to be multiplied together, I just use all the little ends of my branches together to get the things that I need out of it. So I'm going to have this 2 compare up with this 2. It's okay that they're not next to each other. Comes out as a regular 2. These 2's also come out as a regular 2. This guy doesn't have a pair, so he stays underneath. And that's going to give me 11 there. So I get 2 times 2 is 4, and I get 4 square root of 11. Okay, so before we go on, let's talk about how to check yourself if you're unsure. You can check yourself on any of these by taking what's on the outside and squaring it, multiply by what's on the inside. So 4 squared is 16 times 2 is 32. Bam, we're done. When I do that here, 4 squared is 16 times 11 is 176. Well, 22 times 8 is 176, so I'm good. The calculator can do that for you too. You can type in 4 squared root of 2, look at the decimal. Square root of 32, look at the decimal. The 2 decimal approximations should be the same. So it just tells you that they're the same. What it doesn't tell you, either way of checking yourself, it doesn't tell you that you reduced it all the way. It just told you that you reduced it. Because I can reduce this one right here to, let's say that I just took out these 2 2's as a 2, excuse me, but I left these 2 underneath. This could be 2 times the square root of 44. That has the same value, but it's not simplified all the way. So the calculator won't tell you that you finished, it'll just tell you that the values are the same. So you just always want to make sure that you have taken everything out of what's underneath the square root that you can. It is possible that you can still take a tree of this, like this is 11's a prime number. Maybe what's left underneath isn't a prime number, but as long as you can't pull out any pairs, then you're good. Okay, moving on. Now, if we have variables underneath, it says what we're going to do is even exponents are perfect squares. So you divide the exponent by 2 and bring it out of the radical. So let's think about what that means here. I'm going to rewrite it so that I can write it a little bit smaller. But if I have the square root of a to the fourth b to the eighth, okay. I just rewrote it so I'd have a little bit more room underneath. A to the fourth is the same as a squared times a squared, and b to the eighth is the same as b to the fourth times b to the fourth. Now, I could keep on going. I could keep on going and get 4 a's and 8 b's, and then I could take out all my pairs. But just like I said, you could stop up there. I have pairs. These two are identical, so I mark them out, and they just come out as a regular a squared. And I have 2b to the fourth, so they both mark out, and I get b to the fourth. And so a to the fourth, b to the eighth, when I take the square root of it, this is what I have here. So basically, I just took the exponents and divided by 2. That's all that happens. And if you think about what that means, when I square this, I multiply it by itself, that makes the exponents 4 and 8 back there. Now, when the exponents are odd, they're not perfect squares, so you have to split them. You can think of it this way, too. Let's see. We've got, instead of splitting it, I took the 4 and I just split it in half. I'm going to have to make this x squared times x. This is going to be x to the 6th. Oh, not x. Dang it. That would be y to the 6th times y. Okay, and that gives me even ones now. Now when I split those, x squared becomes x and x. Y to the 6th becomes y to the 3rd, y to the 3rd. And so when I go to pull things out now, these guys that had to be singles, they got to stay underneath. It's just going to be the x and the y. And then these two come out as a regular x. These two come out as just a plain old y to the 3rd. Basically, here's in a nutshell what you do with exponents. If the exponents are even, you just divide it by 2 and the whole thing comes out. If they're odd, you subtract 1 and it stays underneath, and that leaves you with the x squared. You divide that in half, this x to the 6th, you divide the 6 in half and pull those out right there. But still just doing the full tree and lining it all out and marking them all out, that works too. Okay? All right, so we've already talked about most of that a little bit. We didn't really talk about fractions though, so let's talk about what happens with our fractions. Because we can't have fractions under the square root, and we shouldn't have anything that looks like this. So when I start with this one, it says, if I've got this whole fraction underneath the square root, put the numerator and denominator into separate radicals and remove the perfect squares. So if you just look at these two examples here, oh no, I'm sorry, this one and this one, or just how these are different. Whether I have this that looks like this, I can split it into square root of 17 over the square root of 144. And here I could put it all under 1. So either way, these two things are saying the same thing. So then I just treat them separately because I can't reduce the fraction. It always makes it easier on you if you reduce the fraction as much as you can. I can't reduce that one anymore. So square root of 17 is just the square root of 17. Can't do anything with that. That's a prime number. Square root of 144 is 12. Now notice I didn't put plus or minus 12, and we had talked about that. It takes a whole complete lesson to explain the difference, but basically if you just take a square root of a number, just the square root of 144, that's what's called a principal root, and it's always positive. If you are solving an equation and I have x squared equals 144, and then I take the square root of both sides, that's when it becomes plus or minus. The whole why behind all that's pretty complicated, but that's why there's a reason I'm not putting it here. I didn't just leave it off. But then this is the simplified version of this right here. Okay, so then square root of 15 over 5, and this is all underneath one big square root. You always reduce the fraction as much as you can. This reduces 15 divided by 5 is 3, so this is the square root of 3. And that's all I can do with it because I can't reduce that anymore. That's that. Now here I've got the square root of 24 over the square root of 8, so that is the same thing as the square root of 24 over 8. And 24 divided by 8 is 3, so that is the square root of 3. Now, there's another little catch with fractions. Okay, so you can make sure that there is no radical in the denominator by rationalizing the denominator. I always tell my kids, rationalizing the denominator sounds so complicated, and it's really not. But if you're working hard on something and somebody's bothering you and they say, what are you doing? You say, I'm rationalizing the denominator, and they'll go away and leave you alone. And then you can impress them because it looks really hard, but it's really, really easy. Let's talk about what that even means and why it's even called that. A rational number can be represented by a fraction. So a fraction, even a decimal, can be a rational number. 0.5 is a rational number because it can be represented by the ratio 1/2 or 1/2. If you take a square root in the calculator, like the square root of 3, that is an irrational number. You get some crazy decimal, it cannot be represented as a fraction. So irrational numbers can't be shown as a fraction. Just think about that. So I need to make them rational. So if you're going to rationalize a denominator, that means you have to make the denominator rational, which means it cannot be irrational. And an irrational number would be like pi or a square root or anything that I couldn't represent as a ratio of two numbers. So when I have this right here, on the one before that, we had a 15 over, or we had fractions and we could just reduce and divide. But this 15 is not under the square root, and the 3 is. So I cannot divide those. They live in two different worlds. That does not become 5 of any sort anywhere. Okay, not at this point. So it says you cannot divide these, you must rationalize the denominator. So you multiply a radical number in the denominator over itself. Here's what this means. Let's say that let's just go back to just fractions in general and forget square roots. If I have to add, let's say that I'm going to add 2/3 plus 5, right? In order to add fractions, I have to have a common denominator. So in order to have a common denominator, I'm going to have to change this whole number. So I pretend like it's over 1. And then my common denominator here would be 3, so I would have to multiply by 3/3, right? And then that's going to give me the 15/3 that I need. Well, because I need the denominator to change, I can't just put a 3 in the denominator. I multiply by 3/3 because this has a value of 1. So it changes that so that it's going to look like 15/3 instead of just 5, but it doesn't change the value. So the same thing happens over here. I want to get rid of the square root. In order for me to get rid of the square root, I'm going to clear this off because I need to move it down a little bit. In order for me to get rid of the square root, the only thing I can multiply the square root of 3 by to make the square root itself go away is the square root of 3. So think about this. Square root of, let me just do 7. Square root of 7 times the square root of 7. Remember we talked about that. We don't say it's the square root of 49. Anytime you multiply a square root by itself, you just get what's underneath. It's just 7. If I multiply the square root of 7 times the square root of 3, I multiply what's underneath, and I just get the square root of 21. Like, that doesn't get me anywhere. But I multiply by that, I can get rid of the square root. So that's what I want to do here. I can't have a square root in the denominator. It's illegal. You can't have an irrational denominator. So that means the only thing I can multiply by the square root of 3 by to make the square root go away is the square root of 3. Well, if I only do that, I've changed the value. But if I do this, this fraction has a value of 1. So when I multiply anything by 1, I'm not changing the value. So when I do this, and then I just multiply straight across. 15 times the square root of 3 is 15 times the square root of 3. They live in two different worlds. Remember, you treat a square root like a variable. So that's like 15 times x. All you can do is 15 times x. And then the square root of 3 times the square root of 3 is 3. Then you reduce the fraction if you can. Sometimes you cannot. But in this case, I can. Here's what I don't do. I do not divide the 3's. The 3's don't cancel out. Square roots live in a different world than these do. But this is like 15x over 3. Think about it as a variable. And I can reduce that. 15 divided by 3 is 5. So this is 5 square root of 3. Okay, so the simplified version of this is 5 square root of 3. You can have a square root in your answer. You cannot have a square root in the denominator. Period. End of story. Okay, so now here's another one. I've got the square root. There's clearly one in the denominator because it's just all one big fraction here. So I'm going to change this like we did on the other page. This is going to become the square root of 4 over the square root of 5. Well, I can take the square root of 4. It's 2. So now I have 2 over the square root of 5. But the problem is I have a square root in the denominator. When you think you're done, danger, danger, don't stop here. We got to fix this. And so I'm going to rationalize. I multiply by the square root of 3 over the square root of 3 here. That wouldn't make any sense here because there's not a square root of 3 in the denominator. You multiply by whatever the square root in the denominator is. So the square root of 5 times the square root of 5. So then I just multiply straight across because multiplying fractions is easy, and I get 2 times the square root of 5 over 5. Now think about it. Do you think I can reduce that fraction any? Can I mark these 5s out? No, I absolutely cannot. 2 and 5 do not reduce. You absolutely positively do not put a decimal. I can't reduce this. This is it. It's ugly, but I'm done, and that is a kind of answer that you're going to need to get used to getting. Okay? So you've got to rationalize the denominator. I will tell you on the next video that you're going to watch with Pythagorean theorem, this comes up, but when I did that video, I hadn't done this with my students yet. We hadn't rationalized the denominator, so I tell them to stop and that it's not legal, but we're not going to talk about what to do on that day. So just FYI, that's why that's happening, because we hadn't been through this yet. But I got to do things a little bit differently with y'all. Okay, so now we're talking about more than one term. So if we have more than one term or have parentheses, if they are like terms, radicals are the same, and a whole number coefficient. They are not like terms, try to simplify the radicals to see if you can. And if there are parentheses, remove them by multiplying using the distributive property or your power rules. All right, so this is something that we had talked about on our other notes, but again, this kind of is a comprehensive set of everything. When I have this, these are like terms, so you think of them like variables. Do not make square roots harder than they are just because they look weird. They look weird, they look ugly, they look very difficult, but they are not. All you do is think about this as 2x plus 3x because they have the same thing on them, or they're things. I have 2 square roots of 5. You give me another 3 square roots of 5. That gives me a total of 5 square roots of 5. Bam, I'm done. Okay, then we have this where they're not like. So this is more like y plus 6x because they're different, right? But I can't simplify this one anymore, but I can simplify this one. So if I do that, 8, that's going to be 4 and 2. So since 4 is a perfect square, that I can take the square root of that. So that really gives me 2 square root of 2 plus 6 square root of 2. So that right there is more like 2x plus 6x, and I can add those. And when I add those together, I've got 2 square roots of 2 and 6 square roots of 2. That gives me a total of 8 square roots of 2. Distributive property. Well, that's just like it sounds. You don't do this any different. Remember, your rules don't change. It looks weird. This could be monkey plus elephant. You distribute the 5 to both of them. It doesn't matter what it is. You need to draw your little arrows, draw your little arrows, right? So 5 times 6 gives me 30. And then 5 times 3 square root of 3, remember, he does not associate with what's underneath. This is just along for the ride like a variable. It's like 3x. 5 times 3x is 15x. So 5 times 3 square root of 3 is just 15 square root of 3. You don't multiply by this and this. And then this is my answer. Now, just like if this was 30 plus, that out of the way here. Just like if this was 30 plus 15x, that does not become 45x. This 30 plus 15 times the square root of 3 does not equal 45 square root of 3. No, no, no. Absolutely not. Just like 30 plus 15x, you wouldn't combine those. You may have when you first learned that stuff, but you should be past that. So you can't do that with the square roots either. Okay, so now we have the power of a product rule. Product means that's the result of multiplication. So when you have multiplication, not addition, multiplication, then you apply the power of product rule. And you should have learned exponent rules in Algebra 1. So what this becomes then is 3 squared times the square root of 2 squared. So then we know that 3 squared is 9, square root of 2 squared is 2, and 9 times 2 is 18. And then another way to look at that also is to know that anytime you square anything, you multiply it by itself. So this is 3 square root of 2 times 3 square root of 2. And again, 3 times 3 is 9, square root of 2 times square root of 2 is 2, and you get 18 either way. If you type this in the calculator, I would not suggest that at all. Even when you're allowed to use calculators with this stuff, it is safer for you to do this not on the calculator, because what happens to the majority of people is that they don't type it in right. They think they're typing it in right, but they're not really, but they're not. And then you just take what the calculator says as gospel and be like, oh, well, that's what the calculator says. It has to be right. And you're not really paying attention to what you're getting. So just make sure that you understand the concept so that you can do it and get it right every time. So let's talk about what this does not mean and what I see sometimes as well. Let's say that we have, I'm just going to make up some numbers here, 5 plus the square root of 7, and we're going to square it. Okay. This is not the power of a product rule because this is not a product. This is a sum because we are adding. This absolutely does not become 5 squared plus the square root of 7 squared. Big fat no-no on that one as well. This you would have to take it and FOIL it, or do the box method, or do distribution, or whatever it is that you learned and that you like. But it is not this right here. It's just like if I had x plus 3 squared. That is not x squared plus 9. Right? I don't get to distribute the squared like that, because that only happens if it's a product and if there's only one term in here. These are 2 terms, so those are big no-nos on that, but that's what's happening here. This type of thing is going to come up a lot, so you want to make sure that you know how to do that correctly. Okay, so use this tip sheet. You're going to end up having to tape it in and not glue it in because of the way that it is. I'll tell you what page to tape it on Monday. But this is something that you probably want to keep handy with you even after this course, so that when square root things come up, you know how to handle them. They look yucky. They're going to intimidate you at first. Don't let them get the best of you, because they are not difficult. You just have to make sure you're not making stuff up along the way. Okay, so make sure you use this and think about what you need to be able to do when you are working the problems on the worksheet that goes with this, so that you've got good practice on this. You need some practice, but after a while, you won't be nearly as uncomfortable with them as you might feel right now.